can say that you divide predictor space on areas. Say if you're falling and the areas are just regular figures like squares or rectangles, because you make a statement if then. If the value of, say, predictor A is less than 1.6, then something, or 1.7, then the result is such. If the value is greater than the threshold, in our case is 1.7, then the values are different. So then there is another division. So now we take into account predictor B, if then, and this singular if then statement, which is extremely easy to understand, is then graphically can be represented as your predictor space is divided into the area. And when you see that, so depending on what are your predictor's values, the outcome is such as depicted here. But of course, you remember that we are doing regression task. Regression task is when you're predicting values, exact numerical values. And we train the model, so we have some subset. And if you know that, say, for the set of predictors like this 1.7 or the whole area, you won't have just one value, say, for solubility. You remember the solubility test. So for this area, you will have some distribution of values. And then the question which one to choose. And the answer is, well, the practice is you can either mean or median. So when you are to choose something from the set, you can choose either mean or median. So you have some distribution, and in that sense, it's not very accurate. But as I told you already, the effectiveness of this model comes not just from one tree, but from the thousand, from ensemble. So these are the rule, and we see the simple rule, and the simple rule means that you just have two splits of data. Two splits that you have one condition for predictor A. There are different outcomes if predictor A is less than 1.7, and for predictor B, the boundary is somewhere here. And the result, that means when you have a boundary, you can see you have splits of the data. Split of the data because the results are different depending on the threshold. And these two splits of the data can be represented into three terminal nodes of the tree. I wonder if I have this. Do I have this tree? So from tree to roots. Finally, you always can draw this as a decision tree. You can represent if-then statement into the decision tree, and each decision tree would go from if-then, 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 and then every path to the node of the tree can be called a rule. And the rule would be when in the decision tree modeling one refers to the rule, it's look like this. If predictor A is greater than something, B is greater than something, then outcome is something. So there are rules. Say, if the weather is good and I have a free day, I will go for a walk. Or you do something. Or if molecular weight of my of the substance I'm studying is less than a certain threshold, and the charge is less than 2, then my solubility would be this. So there are many other. The good thing about trees is that they're really easy interpretable. So they're very easy interpretable. This is what I already told, that weakness of this model instability, and solution ensemble method. Ensemble method that we finished today by the ensemble method. So the basic, the first model we are going to study, I probably will go back and forth from theory to the practice, because for you to try. So the very simple model is a called classification and regression tree altogether. It's with abbreviation CART, as you see it is on the slide. And again, the algorithm is then you try to find the split for each predictors in a set, and you define a set of rules. So if A less than splitting threshold, then the output is 1. If predictor is more than, greater than the splitting threshold, then the output is 2. And because we are solving regression task, we have to minimize some errors. And in that case, when you have just 2 splits, you are treating all 2 different areas separated. So you are calculating errors for 1 split. This is cap is observed and y is predicted, and this is the same. And then the same as in linear regression model, you're minimizing the error. You're minimizing the error, sum of the square error. For example, this is how it looks like for the for the data you already know well. I hope this is solubility data. And if you do it just on one predictor, you look at this. For example, we see this is the dependency or solubility on number of carbon atoms, and then you can have just simple rule if the number of carbon. This is of course normalized, right? Because you cannot have the number of carbon atoms is always integer numbers, but then when you normalize it by the weight, by the number of all atoms in the molecule, you can get the non-integer value. Then you do the simple rule. So you have a split. You have a split by this value, and this is found exactly when you just scan. You scan through all possible number of carbon atoms, and then you see how the arrow, how the sum of the square arrow changes, and then the algorithm can find the split, where to see the split, where there is the minimum value. And then once you, so the algorithm do it, so then it takes another predictor. So we took the first predictor. Then we continue to grow trees with the other predictors, and say continue with the building, going in 2 areas. And then you do it one by one, and we will now see to the more short. You can cut it whenever you want it, or you can do it till the end. But actually, if you have 228 predictor, we don't want 228 splits. We would like to, the fewer split, the better, because it's more interpretable. If you have 228 splits that goes all the way down the tree, it's not very easy to make sense of the resulting trees. And the task is usually to find more simpler rules that best explains the data. And to do so, there is a parameter called complexity parameter. So actually, there is a penalty. We don't want the tree to be very large and branches, so to say. We can calculate the number of terminal nodes and say that the more terminals known, it's worse to have more terminal nodes than less, and introduce some false complexity parameters that you will see as a tuning parameter in the CAT models. And then here you can penalize the similar way as we penalized error in linear regression models. We penalize with the sum lambda coefficient multiplied by the sum of the weights, either in squares or absolute values. And here, similar-wise, you can penalize error, sum of the square errors, by the number of terminal nodes multiplied by the complexity parameters. What else for this model? That's what you get at the end. So the final cut tree would look like similar to this, and probably we will get the same plot in half an hour, maybe less. And that's what I told you. You see the distributions here. That's the problem with regression tree that one has to keep in mind and see if it is worth it to go for it or not. So from one point it is now, because we have a training data. When we train this tree, so for this split, first we have the first split on number of carbon atoms. It's like a major dependence on solubility. With the threshold of 3.78. And then we have other splits, surface area, number of non-hydrogen atoms, hydrophilic factor, and when we end it up, so it's not just one value, one data point that follows this condition. There would be a number of data points in our training set. And because there is a number of data points, actually there are 48 data points, data sets, 48 items, 48 substances that satisfy this one rule goes there. And that's why we have distribution of solubility value here, and then this box plot with medium and other things. And the same for each node. So you have to realize that once the prediction is made, it's not just the one value, it's a median value. It's a median value, and that's why the prediction result is not as much accurate. But when you finally end it up, you have a test data and you end it up here, you have to realize that you're somewhere in the range, because other training data sets have this kind of distribution, as you see on the block spots. And here we have 11 terminal nodes, and here the results, there was a complexity parameter that was a tuning parameter that was chosen by the model 0.01, and RMSE was this value. Now I think we can tune in profile, and relative report. That's what we are going now to get in the workshop. Let me switch to the workshop first and rebuild this. Okay, so I hope that carried package and library applied predictive modeling works, and you didn't forget everything, because we haven't seen each other for 2 weeks. Again, we are still with this data, so you need it here. But today you will need library R part. Partition is from partition, regression partition, I guess that's abbreviation. And once you have this data solubility, you have your soul train X transport and soul train Y. And soul train Y. And please try to install this library. So library R partition. Odds from partition are, I guess, from regression. And then you create another data frame that first copy all predictors, transforms predictors, solve, train, transformed, and add y, solubility, train y, and y as another column by the name y small. Does it work?
Yes.
For everybody? Good. Okay, let's go. Tell me to stop. Now try split. So why is it good again? It's not because it's extremely precise, the algorithm. It is not. Of course it is not. It wouldn't produce you clear, precise predictions. But it is nice sometime before building complex model like neural networks, deep neural networks, or SVM as a black boxes. It's nice to fill your data and to fill your data. What is the, because from in all modeling, usually either it's science or business, the main purpose of the modeling often not to predict values, but to tell what is the most contributors to the prediction, what is the most influential factors, say, what is contribute. So in science means that there is, if some factors have a greatest weight, you know that there is a more association, biological, scientific association. And when you see it in business, then this is a contributor in, in selling or in being inclined, being good. This is the most important parameter you have to look at when you make your further decision. And this model is, in that sense, is very powerful because you can think what is. It's immediately find that, say, here we see that number of carbon atoms is just simple first predictor that influence solubility. So it means that contribution, the weight of this parameter is a number one when you study it with a tree. So this is a part, it's not a train, it's not a carry package, so you don't use train. That's why we created this special syntaxes. So you predict y tilde dot, taking all predictors from the table data, train data, and then, okay, max depth one, meaning that you just find the one split. Once you get it, now please change it to 2, to 3, and see how you add predictors one by one. And see how the
Sorry, one second to previous slide.
Who else has a problem with this? Do you have a problem with this? No. Okay. Hopefully we can catch us later. So try to vary the smart depth parameters. Try to vary try to very much that 2, try it finally split 20. Try finally split 20.
After 5, it doesn't change anything. 5 is enough, it doesn't change anything after 5.
What do you mean?
And max depth 5 is enough to complete the full.
How do you know?
Are you
How
sure
do you
about
know
the
that's
5? I'd say it's like 8.
How do you
Because
know
when I-
5 is not?
When I make
Add.
some more, add
Okay.
more, it doesn't change anything. The model stays the same. So when I try 6, it's the same as 5 and more and more. Divided. And more than 5, it doesn't change.
Shouldn't be so. Should use 20 splits then.
No, first of all, I'm not sure whether we can use 20 splits without using the same predictor several times, because we have only 200 variables, and with amount of splits equal to 7, we will already have all possible variables in our tree.
No, but then when it splits, you can. It's not that they will. You see, they're not that say the level. You have a root number of carbon, then surface area 2, but then the number of. So they're not exactly in the same order. You see, the number of carbon more than threshold, then the second.
Okay, I see. So yeah, we have duplicate predictors in this tree. Okay, then we can use 20. I was wrong.
You can use,
Yes.
no, there is no restriction on how to use, so you can use as much as you want. This is just to explore, so this is a very useful, it's not a parent package, it's an additional package. It's just to explore dependency, explicit dependency with explicit value. Because when you see the split, these are original predictors values. And it makes sense, depending on the task you are doing, it makes sense. Specifically, in the business application, you can see the surface area, or if the square feet for apartment price prediction, if the square feet is less than a certain threshold, or if the number of bedrooms less or more, or something like that. So, because to make a scientific example, it could be more difficult. In terms of class, there are some density, there are something else. But what is most convenient? These are exact numbers that make sense, and this is good. Okay, now we are going to train package. Train package also have this implementation, and let's do tuning. So we have. Again, we will do control parameters with the cross-validation with folds, and then we create this indexing file, and train control method is cross-validation with the options to create folds. And then you do train as we usually do. Train X, Y, and are apart. We say tune length. We'll see now in a moment what is the tuning parameters in that case. We iterate on the end, train control. And then you plot. Remember, you plot it. You plot it as we plot. When you plot model, you get usually plot for tuning parameters. And tell me what is this tuning parameters here in our case. Of tuning parameters, what's the best tuning parameters?
Some complex parameter.
Complexity, do you remember what is complexity parameter? And what's the value of complexity parameter?
0.00299%.
Like this, right?
Yes.
Yeah, this complexity, remember complexity parameters when we finalize form of sum of the squared errors. This is an internal algorithm, so sum of the square errors plus complexity parameter multiplied by the maximum tree depth. So these cut value, if you plot cartoon, you get something like this. So actually, it's the first chosen. It's automatically, right? It's. No.
The second was true. The second was true.
The second, yes. Not the first. I wonder why. Maybe we cannot see it on the graph. Yes, we cannot see it on the graph. The local minimum is here, that is why. So the plot doesn't really reflect all the dots are like in one place.
Would you show the previous thing?
Sure. So did it work for everybody with the chair? Did it work? Yes. work over there? Okay, now we'll try to generate nice plots. For that we need a package called party kit. Again, party from position. And then we use the same module we just built, cartoon. And the final module has a lot of internal parameters which you can access with the dollar sign. And the final module in some form, you can print it and see what it is, this final module. It depends on the realization. It could be either the set of rules or something else. It's not obvious what it is unless you look closely at the results. But you can convert it with this as party. It's meaning you make an object because this object specifically was developed for this model, produced with the part package. And then you plot this tree. You plot this tree as I showed you. You should get something that I showed you on the slides in the class presentation. Of course, you will see it collapse on your small area of plot, but then if you save it as PDF or as GPF with high resolution to have it, you can save it maybe. Try to save it and then reopen, otherwise you can see anything. It's too dense to see something reasonable. You can, when you are saving, try PDF, and PDF works. If it does not, try GPF, but put a high size. Just add pixels, because when you save PDF, you can see how many pixels in your slides. Somebody is happy in the dark old November day. Now, did you get this messy tree first looking, but then, no? Again, the package couldn't be installed. Okay, now you see how to get the idea. So this is real nice to get grasp, to get hands. So to call in your data, let me see if it works. Good. Did it work for you? You're doing Mars, so okay, so no, it's not Mars. It's not Mars. No, I don't have slides for this. No, it's trees. No, we're doing it different. It's Mars. Well, it's two classes in a row. Mars. Okay. Question.
Exactly the same.
Yeah, exactly. So they're just exactly the same, you're right. Okay, this is just for nice plots when you have the report and the next thing that we love about models, some models produce, some models do not produce, variable importance. So variable importance, this is a function called carry package. Var imp I, it's I capital from importance. It's not one L, it's not one, it's var importance. And you have this importance chart, importance table. Okay. Okay, so
Which slide is
it's caret library. If it's you have to load caret library. You have to load caret library for that purpose. And you see it's likely to, so the first split was on the number of carbon atoms, but here, actually the first variable that fall out on the list is number of non-hydrogen atoms. So sometimes the fluctuation happens, but still you can grasp who is the most important contributors. Remember, what are the other models that also can give you variable importance of those that we started? Remember? Who can tell? What are the other models that also produce, or say, linear regression model? Can you get the variable importance from linear regression models? What do you think?
Yes, I think yes, because we have coefficients for each variable.
Correct. Mars model, do we have? Do we have variable importance for Mars? Remember Mars, multi-variance, adaptive regression splines. It's like piecewise linear approximation, Mars model. Can you build variable importance based in Mars model? Yes, you can. Okay, yes, you can. Support vector machine. Can you get a variable importance from support vector machine? What do you think? Yes, in regression, yes, you can. It would be coefficients. Though in classification, they are not with weights. Will come, but in regression, since actually in any regression, what is in a regression model, when you have weights in front, though I'm not sure it's supported here in the carry package variable importance for support vector machine. I don't think so. I don't remember if we checked it, if we tried it. Because it could be that they don't have variable importance on support vector machine. The support vector machine, because you take not only data. Secondly, yes, we will have the coefficients at the end, but not necessarily you can get the variable importance. You cannot get it in neural network though. Here it's difficult. It's difficult to control the weights. So, okay, let's move on. Predict. Yes, please do prediction. Please do prediction as we did for all that. And if you have these numbers written, I would like you to compare how this behaves compared to other models. Try to predict on test. We predict on test. And here is we just did okay, save result in the data frame when the second column called card. And what's next? Let me see what's next. It's actually, well, I would like you to do predictions, so you don't have to repeat this. Do predict as you did it before. Just copy block. Don't do it as I did it on the tape on the desk. Copy your how you do predictions. You save the result with some vector. Then you combine them in a data frame with the column observed and predicted, where the column name are OBS, OPS, and PREP. OPS equal to and PREP equal to, and then you do default summary and you see RMSE and R squared. Do it as we did, just copy block and replace, don't do it as on the table. And tell me numbers, tell me R squared in RMSE.
Well, I wrote RMSE equal 0.8663 and R squared to 0.8269.
But can you compare now to the linear model? Do you have it somewhere
yes,
written?
It's somewhere written.
So what's the RMSE and R square compared to other models? So we built now the rogue model, about 6 or 7 from linear regression, counting with penalization, then support vector machine, Mars neural network, even I guess KNN. Tell me how this prediction fits into.
For instance, it gives less errors than KNN, but it has more error value than, for example, tuned neural network. And so on.
And R square is not that high, 82% compared to 80. Of course, it's a simple tree. It is. So because we predict with the mean values, right? That's the disadvantage. We don't predict the exact value of prediction at the mean value. Of course, the error would be bigger. It's a distribution. That's okay. Did you manage? Everybody managed to get to the default summary? Did you? Maybe it started to install too much of the things, so it's done now. Okay, so that was about one single tree. It's called classification and regression, and the next one is the tree module, which is called M5 module. Let's try it. Let's try it. For that, you need to package our webcam. Hopefully it works. This is the same as you have already. You don't have to type it again. This goes from our last analysis. The only thing you have to, the newest here is to install package R webcam and to install library webcam. Then you don't need to type these two lines because you have them the same from the previous analysis. And then you do M5 methods. M5 methods. No, we don't have this here. Control. This is like this. No, you leave it as it is. This is already, it's the same. It's the same as we used. You don't have to type it. It's the same. You install library webcam and you use package M5. It's a free package. You use the package M5. This is some internal parameters specifically for this package control. We have control and M10. And then as the result, when you train this model, type it and see what it says. Explore what it says.
I'm currently installing our.
Doesn't work?
It's in.
It's with Java, right? Okay, forget about it. It's with Java. No, it's an SF. What is? Java is, no, let's keep it. We never installed Java here in the class. It's really the, yeah, I remember, sorry. No. Okay. No, yes, keep it. It's impossible. I'll send around those lucky guys that have Java working, then we'll have nice code. But no, it's just about code. Okay, so we tried single tree methods, and we see it has some performance, but the advantage is interpretability. Advantages, and here is was M5 that we wanted to try. It's again some reductions, split criterion, but that's not been like now to study, modern stream solubility data, and then if we could get the Java installed, we could get a nice tree, but now it doesn't work, I remember. It did not work last class. So it's just a waste of time because Java is fully correlated with the ARM. Started to be, but then so it just remember if you are thinking about single tree and you know how to run an R parts, there is an M5 module that you can read additionally, and even you can generate nice plots, but it takes time. It's not that easy. The plot will tell you here, for example, this is a nice, here you have exact values, and here you have criteria for splitting the data. So this is, but our part also is fine. Okay, this is the linear coefficient plots for the module because we do regression. You can always generate this plots for different model and explore either the weights or coefficients are positive or negative. We don't do it in the class. What I would like to continue with is the ensemble methods. Again, ensemble methods. What's the idea? Idea is that you do not know which set of predictors to choose and build the model. For that, you randomly, bagging. The first method we use is bagging. Bagging actually used not only for trees, but for any type of model. And carry packets, I'll show you in several minutes that carry package contains many bagging type models, not specifically based on the tree. But here today we started bagging on tree. And bagging comes not from the bagging, but from the, it's abbreviation from bootstrap aggregation. That tree is just bootstrap aggregation. Bagging is bootstrap aggregation. What is bootstrap aggregation? The first question is, what is bootstrap? What is bootstrap?
Method of resampling.
Say again, please.
Method of resampling.
Method of which type of resampling? What precisely? How you do resampling when you do bootstrap?
Just taking groups, different groups of.
For example, you have 100 samples. How you do bootstrap resampling? Will it have the same 100 samples or less?
No, will be will have less.
No, it will have 100.
Not 100, but
We're running even samples from the whole sample, and samples can be repeated in the final sample.
Correct. It's called sampling with replacement, meaning you take a number and you put it back. So, for example, you have 100 samples. We have a numbered ball in the bag. We put our hand inside the bag. We took a ball with a number. We write it down and put the ball back in the bag. Back in the bag. And then I can randomly take the same number. So this is what's called bagging. That's what we do here. So we create different samples with predictors. Say we have our 228 predictors on our solubility data, and we create many bootstrap samples. So some predictors are just taken twice or thrice or 5 times, depending on your random choices. Some just fall out, and then you build tree without some predictors. So it's a random choice, and you build a decision tree. The algorithm to build one tree is exactly the same as we just played with one tree, but then you do it thousands of times. You can have thousands of predictors, thousands of trees, and then you take an average over all tree, and that would be your result. So the algorithm is very simple. Say you have m iteration. You generate a straight sample from the original data and then train unprime tree model on the sample. This is what it's going to do. You do it m times as many trees, and then you generate the trees. And then let us see. This is actually, and that's what I told. So you can do bagging. Bagging is a play with predictors. It's not specific to the tree. So you can do it to the card. So you play cards classification and regression, and you can do it with the backed card. You can do it with a Mars model. Here is simulation how you do it with a Mars model. And if you go to the if you go to the internet and if you go to the internet and type carrot package methods, and we have carrot package, and you get a list of all carrot package methods. And then you search for the bag here, bagging. You can see no, it's not that page I wanted to wait. Package models, not methods, maybe models, package models. A list of available models, yes, list of available models, and then you can look for web, other boost we will start. Backed card, you know what it is. This is actually what we are going to do in a moment. Then you have backed FDI, flexible discriminant regional studies. Yes, it's for classification. Backed logic regression, probabilistic regression. It's again for classification too. You see there is a backed Mars. You have just backed model, any model. So it's not, this is what I wanted to show you, it's not just dependent on the model. You can do bagging with any kind of model. But now let's try to do bagging on trees. Free bagging, and for that you don't have to install fortunately anything, and method is called just tree bag. That's simple. Just to save time, we'll try only 50 trees, number of bagging features. It's not in practice. Usually you have to do thousands or 2,000 to get reliable results. But we don't have time to test it to the class, and we restrict ourselves only to 53s. Sorry. And then again, look and finally plot it, CNI, finally. Do I have something here? Just, yeah, this is our MMC rough square inside the trend. I would like you to predict, so nothing to plot. There is no tuning parameters. There is no tuning parameter in the bedroom method. It just you take different number of predictors. But it would be interesting to see what does the model say. The model says that, again, cross-validated only one values and one R squared is given because the method just doesn't have tuning parameters. If a number of trees is not a tuning parameters, you have to explicitly provide it. Number of values. But then please predict, because this is our initial training. Here is, please predict default summary and tell me, here is a quite, well, R square is not really high on train set even, but 53 is not enough, and, but RMSC is low, right? We have, it's always more than one or no? What is our minimum RMSC level? Or is it high? It's probably high. You have all these things.
The previous MSC, the model was dot 85.
85. So this is a high RMSC. This RMSC is high. Is high, but so the test should tell me what is the result for the test set. Is it worse than on the train or better or the same?
Worse.
Worse. How much?
RMC is 0.85. It's a bit
It's better. 85 is a better in RMC. The smaller the error, the better.
I mean, it's better.
RMSC that R squared. Nothing would be strange. Even the train, now we don't need transformation. Because now you don't need this, so you can try that. And now maybe random forest. No, predict is the first model, then the test set of predict. You have it from the previous year's conformity. You cannot find. Okay, trigger 2, this is your model, then former, then you predict from test set. So test X comes. Everything but test. And then you name it in one. No, you predict from test. Not on training. You predict from test. Then you combine a letter frame, which has one column cat, like the picture, another column called forms. So you don't have it somewhere. Really show me any of the previous, any of the when you post somewhere. No. Okay, so you see the previous model on test. Then you create a frame, box script, and full summary. You just copy the block. Okay. Okay, now we tried that, and I think we need a break before going to random forest because it's not sure. Okay, we do a break. Now actually 7:35.